So therefore, I am now going to move ahead and discuss what is known as the 2's complement method representation actually. Complement 2's complement representation. There is something which is also known as a 1's complement representation, and one very important part of learning is the ability to read a textbook, right? And I would like to re-emphasize that in this course, and therefore some small portions like this I will offload it to the student or the viewer to go back and read and understand about this. So 1's complement representation, right? Complement representation is self study. Go read about it. It is available in the book, the prescribed textbook by Morris Mano, Digital Systems. Please go read about this. It's also available on numerous websites. You can search about, search for it and understand it yourself. Okay. So I am going to be talking mainly about a more interesting system called the 2's complement representation for signed numbers, right? So you can represent, as with the sign magnitude, you can represent both positive numbers and negative numbers, but the bit that is being used to represent, let's say the sign is not, in the uh, traditional, in the traditional sign magnitude way. Okay, it's going to get used very differently. So for that, let us go back and look at our analogy that we used in order to describe the binary system in the first place, right? So if you recollect from the electronic systems thinking course, right, I basically said you can consider a balance like this. Okay, so this is the center of the balance, and about that you are going to place a weight here in red, which is an unknown number. Okay, this is an object whose weight could be 1, 2, all the way to 15 kgs. Any integer. We are not worried about fractions at this point, right? And then I said on the right hand side, what you are given is, you are given just 4 1 kg blocks. Okay, so you have 1, 2, okay, 1 kg into 4. Okay, so what you do, I want you to now find out, what weights should be placed on the right hand side of this balance, so that the weighing scale actually is flat. Okay, thereby saying that the unknown weight W is so and so. So of course, if I have a balance like this, which is placed at a distance exactly like this, if this is X, right hand side is also X, right? Then of course what I would get is, effectively I can measure only weights of 1, 2, 3 and 4, because I could place one weight here, or 2, 3, 4, and I could measure weights up to 4 kgs. Now that's not useful. I need to be able to measure weights up to 15 kgs in integer steps. So therefore we said that you have a slightly modified balance. Okay, this is, maybe I'll move this a little bit and then redraw this to reasonably to scale. Yeah, okay. So this is also X, okay, and then at 2x I have another balance here, and at 4x I have another balance here, right? So I told you that this was the right hand side 0, 1, 2 and 3. Okay. And I have 4 weights that I need to place. Okay. 1 kg into 4. So we had discussed that for the unsigned numbers, you can represent any number from 1 to 15 or 0 to 15. 0 is trivial. 1 to 15 as a weighted sum of power of 2 numbers using this 1 kg block. Either the 1 kg is there or it is not there. If it is there, it's like a binary bit 1. If the 1 kg is not there, it's like a binary bit 0. So therefore, the unknown weight W was represented using a weighted sum on the right hand side Rj 2 power j 0 to 3. Okay, so basically we said that in order to, the physics of this is the W into x should be equal to the Rj times the 1 kg into the distance, right. So I would simply multiply this by x and therefore the x would cancel and this is what I would get as the binary unsigned representation of the weight W. So you calculate depending on where you have to keep the weights, you will figure out what the exact weight is using this power of 2 summation, right. Now I am going to try and extend this analogy to a negative number, okay. So the first question that we need to ask ourselves is, what is a negative number in this connotation? Okay, in this setup here, I have a weighing balance, okay, I have a weighing balance like this and I am trying to figure out what is a negative number in the first place, okay. So, any positive weight on the right hand side, if I put a 1 kg, it is pulling it down, right. Likewise, on the left hand side, if I put a weight W, that is also pulling it down, right, on that side. So, essentially it is whatever is acting in the direction of gravity, right, we are basically saying is a positive number, okay, loosely, right. So, what is a negative number? In some sense, if I place a weight W here on the left hand side, right, then the moment downwards is W into G, gravitational force, into L into X. Now, if I want to have a negative number, I need to have something that actually pulls my the weighing balance the other way. This is negative, whereas this is positive, right. So, I have some force that is actually pulling it upwards, right, and therefore I need something else to counterbalance it, right. So, that is the first of all the notional definition of what a negative number could physically mean in this context, right. So, therefore, I am going to say that anything that is going to pull my left hand side up, right, is effectively like a negative number, right, and that is what I am going to try and represent. So, what is a negative number? So, let me just maybe copy this whole setup again, right. I am going to copy this entire setup, go to the next page, right, here I am, okay. So, now what I am going to do is, instead of placing the block here, I am going to place the block on the right hand side, right. I am going to place the block on the right hand side here, okay. So, if you look at this, if I place the red block on R0, obviously that is going to pull it down, that means the left hand side will go up, that is effectively my negative number, right. So, I am going to ask you a question now, right, saying how do I balance this 1 kg block, right. I cannot place anything on the left hand side L0, let me call this as L0, the other ones are, right hand side 0, 1, 2, 3, R0, 1, 2, 3. On L0 I cannot place anything, but now I need to balance these two sides somehow. Okay. So first of all, let us look at, how we could do this, right? If I am not allowed to place anything on L0, right, then what should I be doing? If I place any block on R1 or R0, right, or R2 and any combination of the blue blocks, 1 kg blocks on R0 to 3, the balance would only tilt further to the right. It would tilt downwards on the right hand side, it will go further up on the left hand side. So clearly I cannot do just with this. I cannot make the balance even by adding weights to this system. Okay. So clearly if I have, a representation which can handle unsigned numbers, and I want to handle signed numbers of the same range, it is clear that I cannot do it with the same number of bits because of what you saw. I cannot do it with this setup. I need to do something else. So what I am going to do, I am going to add something now. I am going to add one more balance here. Okay. Except that now, remember, this is 2x and this distance is 4x. So R0 is at a distance x from the center, R1 at 2x, R2 at 4x and R3 at 8x. Okay, I am not drawing the left hand side to scale, and what I am going to do now is I am going to add this guy at a distance of 16x. Okay, and I am going to now increase my weight out here 1 kg. Okay, I am going to increase from 4 1 kg blocks, I am going to make it 5 1 kg blocks. One of those 1 kgs will be used on the left hand side. Okay, so now what I will do is, if there is a block that is placed on R0, and I know obviously that by placing any 1 kg block on R0, R1, R2, R3, the balance only tilts further in the same direction, there is no use going that way. What I need to do is to first place the 1 kg block on this, let me call this L1, on L1. Okay. So now I am faced with an interesting problem, right? I can do the following. I can now go ahead and place certain blocks on R0, R1, R2, R3, so that the combination of the red block along with what I place on the right hand side will balance out the block that is sitting in L1. Okay. So first of all, let's just take one step back. Let's assume I have no block being placed here. Okay, I have no block being placed here. It is just an empty, weighing balance. I have placed 1 kg on L1. So in order to balance L1 with 1 kg, the best I can do is to place 4 1 kg blocks on all these. Okay. So if I did this, right, then the moment, in physics, right, the moment that results because of this is 1 kg into x, 1 kg into 2x, 1 kg into 4x, 1 kg into 8x, right, and therefore this is equal to 15 kg into x. On the left hand side, I am going to have 1 kg into 16x. Okay. Now clearly the 16x, because I have 16 kgs on the left hand side, it is going to be heavier than what is on the right hand side, right? And therefore, there is no way that the two sides will even balance out, okay? So, in some sense, if I put a 1 kg on the left hand side on L1, then I need to put some non-zero weight on the right hand side to even balance that out, okay? So, therefore, let's say that W that I am trying to measure was 1 kg, right? In that case, what I will have here is the 1 kg that comes from the red block into X, right? And of course, I will find that 16 is equal to 15 plus 1. 15 plus, let me color code that, plus 1 kg. Okay. So, now I will say that if the red block that I wanted to measure was 1 kg and I put it on R0, and it turned out that I needed to put the 1 kg on L1, R0, R1, R2 and R3, right? Then I say this block, effectively represents the number -1. It represents the number -1, okay? What does that mean? It means that if I had put it here with somehow magically creating the effect that it was trying to pull the balance upwards, then that would be a -1 for me, right? So, therefore, that is the effect that I am talking about, okay? So, effectively, right? So, effectively, in order to measure, in order to represent negative numbers, what we are going to do now is we do the following, okay? I will again make a copy of this, okay? So, I am going to place the unknown block, I am going to place the unknown block on R0, okay? And I know that I have to put a weight on L1 because I have no choice now, right? Then what do? I am now trying to find the combination of R1, the blue 1 kg blocks on R0, R1, R2 and R3 such that the weights will balance out each other correctly. So, in general, what you will see, right, is L1 into 2 power 4 or into 16 should be equal to my unknown weight into X plus the combination of the weight that I put on the right hand side, Rj into 2 power j, right? Rj is either 0 kg or 1 kg, right? And L1 is, of course, L1 is also like that. L1 is element of, let me write that here, L1 element of 0 or 1 kg, right? And effectively, therefore, my number, right? Of course, there is also multiplication by x which I have forgotten, and now that can all cancel here, which implies my number W that I am looking at, okay, is going to be 2 power 4 minus summation j equal to 0 to 3 Rj 2 power j, okay. So, effectively, this is the idea of the 2's complement representation, okay. The idea is very simple. We are going to represent a negative number, okay, as the difference between the 2 power, in this case 2 power 4 and the combination that actually results. So, let us take a concrete example, okay, and look at this. Let us say that the weight I am trying to measure happens to be 3 kg. Okay. We know that this balance will even out only when the weight on the right hand side totally is 16 kgs, right. So, we know the condition, we know that 2 power 4, right, or 16 should be equal to the weight plus the summation rj 2 power j. Okay. So, now what we are saying is, if W happens to be 3, we said 3 kg, right, this is 3 kg, then I know that this residue has to be 13, only then. So, effectively 3 can be written as 2 power 4 minus 13, right, or minus 3 can be written as minus 2 power 4 plus 13, right. So, effectively what I need on the right hand side is a combination on R0 to R3 which will give me 13 kgs. So, what should I do? I just need to put a combination, convert 13 to binary, and what will you get? You will get 1101, right. So, I'm saying 13 is equal to 1101, which is basically 2 power 0, 1, 2, 3, right. This is 2 power 0, 2 power 1, 2 power 2. So, how much is this? 0, 1, no, this is 2 and this is 3, yeah, correct. So, 12 plus 1 equal to 13, okay. So, therefore, we are representing minus 3 as a number that we are going to subtract out from 16, okay. So, one important thing we already notice is that the moment you assign a certain bit in order to handle signed numbers, you can only measure a smaller range of numbers compared to the unsigned numbers. Okay, so we will come to that in some time, but in general the 2's complement number, right. So, effectively eventually the representation is the following, right, minus W, okay. If the weight was placed on the right hand side, right, then it is a negative number, and equivalently if it was placed on the left hand side with a magic way to pull up against gravity, right, then that would be 2 power 4 minus 2 power 4 into L0 plus summation Rj into 2 power j. Okay. So, this combination of L0, R3, R2, R1, R0 is what is the 2's complement representation of your number, positive or negative. Okay. So, for example, in this previous example, what did we get? We said we wanted to find 3 kg. We wanted to find a represent minus 3 kg, right. So, what would you do? So, let us look at that, okay. 3 kg, what should this be? L0 should be 1 kg, okay. R3 we know here, right, what is it? 1101, 1101. So, this is the 2's complement representation of minus 3, the 3 kg on the right hand side. Okay. Now, you take another example. How would I balance example 2 if this was 5 kg? Then the only way to get this 5 kg balance out with 16 is to make the combination on R0 to R3 11, because 11 plus 5 will be 16, then the balance will be okay, and therefore 5 kg on the right hand side can be represented as again 16, L0 should be 16 minus, that is minus 16, right, and the right hand side R3 to R0 should give you 11, right. 11 can be written as 8 plus 2 plus 1. So therefore 1 0 1 1. This is the 2's complement representation of minus 5. Okay. Now let us come back and see how do we represent positive numbers in this, right. Now suppose, again let me make a copy of this, because remember the representation should be convenient for both positive and negative numbers. Okay. So now I am going to take all this off, even the block and all that, and I am going to put it on the left hand side here. I am going to put it on the left hand side here. Okay. And let us say this is 3 kg. So I am now talking of a representation in 2's complement for plus 3, because the block is sitting on the left hand side, right, and therefore the moment you put something on the left hand side on L0, L1 cannot have anything, because we already saw, if you remember earlier, when L1 had 1 kg, even if you put 1 kg on R1, R0, R1, R2, R3, L1 will be heavier and it will pull it down. So therefore, in order to represent a positive number, the general rule is very clear, L1 must be 0. L1 must be absolutely 0, right. Only then I can find a way to balance the other two somehow, right. Now how do I get the 3 kg balanced? I have to make, I have to do the following. Oh, why is this? Yeah, sorry. So I will just complete this. Yeah, what I need to do now is, if I want to balance a 3 kg, I put R0 equal to 1 kg and R2 equal to 1 kg, R1 equal to 1 kg, right. So this is 1 plus 2 equal to 3. So plus 3 or 3 kg on the left hand side is equal to, very simple, your L1 has to be 0, then R3 has to be 0, R2 has to be 0, and R1 and R0 have to be 1 each. Now let us do the corresponding other example. What if this were plus 5 kg? I will not put a plus here because we are talking on the left hand side. 5 kg on the left hand side. Okay. This is going to be, again I need to have 5 here. 5 can be written as 4 plus 1. So if you convert, how do you balance 5 kg? You got to put something on R0 and then another weight on R2, because that R2 will get multiplied by 4, R0 by 1, and therefore you will get. So the representation here will be L0 has to be 0, R3 has to be 0, R2 has to be 1, R1 has to be 0, and R0 has to be 1, right. So effectively this is the 2's complement representation intuitively from just the weighing balance example that we constructed. Okay. So that is one interesting exercise here, right.